We already know that if two positive charges are brought together, they will repel each other. When two negative charges are brought together, they will repel each other. But if a positive and a negative charge are brought together, they will attract each other. So the question is, with how much force do these charges repel or attract each other? So Coulomb's law is going to help us have a quantitative analysis of the electric force, and it will enable us to calculate the electrostatic force of repulsion or attraction between the charges. To begin with, let us consider two charges Q1, okay, two charges of magnitude Q1 and Q2 placed in a medium. So we have charges Q1. By the way, we are talking about point charges. I'll talk about why we use point charges in a later chapter. So we have 2 point charges, Q1 and Q2. Just want to make them unique. So Q1, Q2. Let's assume all these charges are positive. And from all we know is that these charges are going to repel each other with a certain force. So let this be the force on Q1 due to Q2. This be the force on Q2 due to Q1. I'll write that in a moment so that we keep using this notation. This is the force on Q1 due to Q2, while F21 is the force on Q2 due to Q1. Now, by Newton's third law, the magnitude of the force F12 must be equal to the magnitude of the force 21. We'll prove that in a moment, but this is a very important concept because electrostatic force is mutual. If Q2 exerts a force on Q1, Q1 also exerts a force on Q2, so things remain constant. Now let us look at Coulomb's law. Well, Coulomb's law, like we said in the beginning, is a law, a mathematical relationship that helps us to find the magnitude of the force acting between the charges, and this law was put across by Charles Augustin de Coulomb. Okay, most importantly is the law, so let's go to that. Coulomb's law. Now, with respect to the two charges that we have just seen, Q1 and Q2, according to Coulomb, or Coulomb's law as a formal statement, the force between two charges is proportional to the magnitude, the product of the magnitude of the charges. So force or electrostatic force is proportional to the product of the charges, of the magnitude of the charges. To be more specific, this is magnitude because we will not consider the polarity of Q1 and Q2. Coulomb's law also goes ahead to say the force between the charges is inversely proportional to the square of the distance between the charges. In this case, I'll add another element. Let's assume the distance of separation between the charges, okay, is a distance r. So according to Coulomb's law, the force is inversely proportional to the distance. Force is inversely proportional to the square of the distance or of the separation between the charges. To put these two factors together, we'll have the following. So the full-scale Coulomb's law is that the force, electrostatic force between two charges, is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between the charges. This is Coulomb's law. To make it mathematically viable, we have to get rid of the proportionality constant. So for that matter, we'll have the force being equal to, now because we get rid of the proportionality sign, we must introduce a constant. Let me call that k. Then q1, q2 divided by r squared, where k is a constant. And this constant depends, so k is a constant which depends on the nature of the medium where the charges are placed. Remember our original assumption, we said consider two charges, q1 and q2. Okay, we had to consider two charges, q1 and q2, placed in any medium. So the electrostatic force depends on the magnitude, the product of the magnitude of the charges, and it also obeys the inverse square law, but also the constant of proportionality between the force and the charges is dependent on the material in which the medium in which the charges are placed. And through experiments, it is found that k is actually equal to 1 over 4 pi epsilon, where epsilon, this is a Greek letter called epsilon. It's a Greek letter called epsilon. So where this, in this case, stands for the permittivity. We'll talk about this later. The permittivity of the medium. Epsilon is the permittivity of the medium, and it is measured in farads per meter or Coulomb squared per Newton per square meter, like that. The choice is yours, but both units can work. We'll explore more about the permittivity of the medium later. So the force F from the formula F equals K Q1 Q2 over r squared, where k is 1 over 4 pi epsilon. F is in newtons when Q1 and Q2 are in coulombs and R in meters. So this is very important. Every time we use Coulomb's law for numerical problems, we have to make sure Q1 and Q2 are measured in coulombs or converted to coulombs, and we also have to make sure that R is measured in meters. So just a simple laboratory activity to prove Coulomb's law. Lab activity. Oops. If we have a well-insulated surface and we have a force sensor on both sides, and we have metallic spheres connected. Okay, I think I have to make another color here. So this is a force sensor. These two. This A and B are metallic spheres. So if A and B are charged oppositely, that means if A is given perhaps a positive charge and B is given a negative charge, there will be a force of attraction between the two spheres A and B, and the force sensors are calibrated to give us the magnitude of force between A and B. In this activity, if we add more charges to A and B by any method of electrification, perhaps by contact, if we add more charges to A and B, you realize that the force between A and B increases as we charge up A and B more. Also, we can try to investigate what happens to the distance between the two spheres, which is R. If we increase R, then the force reduces rapidly. So this shows us that indeed the force is proportional to the product of the magnitude of the charges, and it is inversely proportional to the square of the distance between the charges, which is a good proof for Coulomb's law. Also, if we are to plot graphs to demonstrate Coulomb's law, you realize that, if we have the electrostatic force, then we have Q1 and Q2, you realize that the force increases as you increase the magnitude of Q1 and Q2, then the force reduces very rapidly. The force reduces very rapidly if we try to change the distance between the charges. So force is proportional to the magnitude of the charges, but it is inversely proportional to the distance between the charges, or the square of the distance between the charges, to be more specific. So until now we have discussed Coulomb's law and how to calculate the force between two charges. Now let us see the different use cases of Coulomb's law, especially the most common ones. So if the charges are placed in air, then epsilon will be equal to epsilon naught, where epsilon naught is called the permittivity of free space and epsilon naught is 8.85 exponent negative 12 farad per meter. This is very important. So the force between the charges in this case is 1/4. Okay, to write it the basic way, K Q1 Q2 over R squared, which is equal to 1/4 pi epsilon naught R squared Q1 Q2. So this is commonly used because in most cases we'll have our charges placed in air. And because of this common usage, if F equals 1/4 pi epsilon naught times Q1 Q2 over R squared, if you substitute epsilon naught equals 8.85 exponent negative 12 in 1/4 pi epsilon naught, you'll have K equals 1/4 pi epsilon naught, which is going to be, you can plug in this value into the formula here, you'll get about 9 times 10 to the 9th power. Of course the units change per farad meter. So for charges placed in air, we precisely use this common form of Coulomb's law, and we say that the force is simply 9 exponent 9 times Q1 Q2 over R squared for two charges placed in air. Let us proceed and write Coulomb's law in vector form. In our previous study, we have only looked at the magnitude of force without taking into consideration the direction of the force. We will now write Coulomb's law in vector form. So there we go. Coulomb's law in vector form. Let us consider the two charges that we had at the beginning, Q1 and Q2, all of them positive in this case. We have the force, the force on Q1 due to Q2, it's a vector quantity, so I indicate this. Also we have the force on Q2 due to Q1, it's a vector quantity, so I indicate that. Also in this case I indicate the directional vector, the directional unit vector. In this case we have R1 2, R cap 1 2, also R cap 2 1. These are the unit directional vectors of the direction force. The distance between the two charges is R, so I indicate that here too, where R1 2 cap, this is the unit vector from Q1 to Q2, R cap 2 1 is the unit vector from Q2 to Q1. Okay, nice. Let us now rewrite Coulomb's law in vector form, having all this in mind. So Coulomb's law will be written as follows. The force on charge 2 due to charge 1 is going to be given by K Q1 Q2 divided by R squared, and here we'll have R cap 1 to 2 because we have to consider the direction of the force. Oops, this is a vector quantity, so I indicate that. Also the force on 1 due to 2 is going to be K Q1 Q2 divided by R squared R21. Oops, this is a mistake. Okay, we've got to have 1 2 here, not 2 1. Then here we have 1 2. Okay, that's better. So there we go. We also know from the study of vectors that R21 is the same as R21 divided by the magnitude of R21, where R21 is R2 minus R1. Consequently, R12 is R12 divided by the magnitude of R12, where R12 is equal to R1 minus R2. From these two expressions, it is evident that R12 or R21 is equal to negative R12. That means R cap 21 is also equal to negative R12 cap. Let us substitute these two expressions. So let us substitute these two expressions into the formulae for electrostatic force that we have just stated, this and this. Okay, so there we go. I rewrite them again. F12 is equal to K Q1 Q2 over R squared R12 cap. This is going to be written as, okay, this is K Q1 Q2 over R squared into negative R21, if you like. That means F12 is the same as negative F21. So this shows that electrostatic force obeys Newton's third law, because the forces are equal and opposite. Okay, very important. Next, let us explore the concept of absolute permittivity and relative permittivity. Absolute permittivity and relative permittivity. So literally every time we have talked of permittivity, what we actually meant was the term absolute permittivity. The permittivity of a medium is what we call the absolute permittivity. Intuitively, permittivity is the ability of a medium to permit or to allow electric forces through it. The ability of the medium to allow electric forces through it. Air or vacuum is best known to do this because it has one of the highest permittivities that we can always know. So from the formula F equals 1 over 4 pi epsilon naught, 4 pi epsilon times Q1 Q2 over R squared. Let's try to make epsilon the permittivity, the subject of the formula. What will that become? Okay, this case, let's see, we'll have F R squared 4 pi divided by Q1 Q2. This is going to be 1 over epsilon, so epsilon is going to be Q1 Q2 over F R squared 4 pi. So the units will be Coulomb squared divided by newtons and meters squared. So this is where we get the units. Okay, there we go. The units of permittivity being Coulomb squared per newton per square meter. Sometimes we use farad per meter. Okay, I will not derive this unit for now because it involves a study of capacitors, but we'll commonly use it as opposed to the previous unit, farad per meter. That's also another unit for permittivity. So the permittivity of a medium is also called the absolute permittivity, and it is the measure of how much electric force that material can permit to pass through it. Let us now talk about relative permittivity. Since it is generally difficult to measure the absolute permittivity of a material without any reference, relative permittivity becomes a very important and common measurement when it comes to the permittivities of all media. So relative permittivity is the ratio of the absolute permittivity of the medium divided by the reference medium, which is the free space or the vacuum. So this is divided by the permittivity of free space or the permittivity of vacuum or air. Let us use epsilon r for relative permittivity. The absolute permittivity is epsilon and the permittivity of free space is epsilon naught. This is very important, and sometimes epsilon r is also called the dielectric constant, because, as we have already discussed, the permittivity depends on the nature of the medium, which medium is quite often a dielectric, some sort of insulator, and so it is logical to call this term the dielectric constant. Sometimes we use K, sometimes we use epsilon r. I'll use epsilon r throughout the course. Let's look at the relationship between electrostatic force and the relative permittivity. So we have already discussed that for charges placed in air, if we have two charges placed in air, then the force between those charges will be 1 over 4 pi epsilon naught Q1 Q2 over r squared. If the charges are transferred to a medium of relative permittivity epsilon r, remember epsilon r is equal to epsilon, the permittivity of the material, over the permittivity of free space. So the permittivity of the material is epsilon naught epsilon r. This is very important. So the electrostatic force, the electrostatic force in this case in a medium of relative permittivity ER is going to be 1 over 4 pi epsilon q1 q2 over r squared. Notice this is epsilon naught, they are different. This is the same as 1 over 4 pi epsilon naught epsilon r q1 q2 over r squared. So if I call this equation 1 and this equation 2, if we take ratios, in this case we'll take the ratio of F. This is the force, the electrostatic force in a medium, so let me call it Fm. The electrostatic force is in a medium, which is different from F, the electrostatic force in air. So I'm going to take the ratio F to Fm, and if I do that, I get the following result: F divided by Fm equals the relative permittivity. You can try that out more detailedly. So the force in a medium is given by 1 over epsilon r times the force in air. This is a very important relationship because it tells us that if the charges are transferred from air to any medium, when the charges are transferred from air or free space to a material of relative permittivity, epsilon r, the electrostatic force reduces by a factor epsilon r. As you can see, the electrostatic force in a medium is 1 over epsilon r times the electrostatic force in air. If we take an example of water, let's take this. Water and salt. By salt we mean sodium chloride crystals. Sodium chloride is an ionic compound where sodium ions are positively charged and chloride ions are negatively charged, and these two charges are being bound together by electrostatic forces. So air has a relative permittivity of about 81. So if a sodium chloride crystal is transferred to water, just like this, if the sodium chloride crystal is transferred to water, the electrostatic force between the sodium and chloride ions is going to be approximately 81 times. So this is the force in water. It's going to be about 81 times less than what the force was in air, and so sodium chloride will easily dissolve and dissociate because the force has reduced by a factor of 81, 1 over 81 of the force that it was between the crystals, between the atoms, the ions, when the crystal was in air. So this explains why sodium chloride and probably many other ionic compounds will dissolve in water, because the electrostatic force between them reduces. So this explains why most ionic compounds dissolve in water. It is because the electrostatic force between the ions reduces. Okay, so suppose we have a system of charges placed in a certain medium. In this case we'll consider air, and all these charges are exerting forces on each other. How do we calculate the resultant force? So next we'll look at the superposition principle, or the principle of superposition, to help us calculate the resultant force for a system of charges placed in the vicinity such that they can all exert forces on each other. So let us consider a charge Q0 placed in the vicinity or in the space of other charges. Let's have Q1, Q2, and many other charges up to Qn. So there we go. I'll illustrate this with a diagram. We have a charge Q0. Let's assume it's positive. We have Q1 here, Q2 here, Q3 here, and many other charges up to Qn. These charges, let me give them some polarity. Let this be negative, let this be positive, positive, and maybe negative here. The electrostatic force between Q0 and Q1 is going to be a repulsive one. So the force on Q0 due to Q1 is going to be force of repulsion. There we go. Between Q2 and Q0, the force is going to be repulsive too. So this is the force on Q0 due to Q2. Okay, I should have write F, the force on Q0 due to Q2. In this case, the force is going to be attractive, like this. So this is the force on Q0 due to Q3. And finally, the force between Qn and Q0 is going to be attractive. So the force on Q0 due to Qn. Our goal is to find the resultant force that is acting on Q0 after different forces in the system have acted on it. So let's go ahead and do that. Our goal is to find the resultant force. Let me call this resultant force F0, the force on Q0. So according to the superposition principle, according to the superposition principle, the force, the resultant force acting on the charge Q0 is going to be equal to the sum of all the forces acting on the charge Q0 in vector form. So the resultant force F0 is going to be equal to F01 plus the force acting on Q0 due to Q2 plus the force acting on Q0 due to Q3 plus many other forces plus the force acting on Q0 due to Qn. And this is what we call the superposition principle or the superposition theorem in as far as electrostatic force is concerned. Notice that in this case I'm using the vector form of force, so I don't have to worry about the direction. Everything will be taken care of. In the next section, we'll look at several numerical examples in 1 dimension and 2 dimension of how to apply the superposition theorem to find the resultant force on a charge due to a system of many charges.